Professor Krauss,
Yeah.
you say religion is the only way to make a good person do a bad thing. But don't you think you could turn that around and say, well, religion helps a lot of bad people to just be better and do good things? I mean, speaking for myself, I'm not a great person, but I'm a lot better because of the influence of Christianity has on me.
Yeah, absolutely. Look, you can't deny that religion serves many good purposes in society. There's no doubt it brings people consolation at hard times. It brings people together in groups often and gives support groups. So, you know, it is indeed stereotypical to try and label it. My point is that we pretend that religion only is the basis of morality and leads to good things, and sometimes it does. But a lot of the times, and again, if you read the Old Testament, it's one of the most immoral books ever written.
Okay, I'm going to go to another question.
Very quickly, with respect, I think it's religion's the only way you can have an objective set of moral values.
Why?
And if you well, what else would you suggest as an objective set?
Reason.
Okay.
It's a beautiful picture from the Hubble Space Telescope of a distant galaxy, far, far away and long, long ago. And there's a whole galaxy, it's about 1 billion light years away. We're looking at it as it looked 1 billion years ago. So many of those stars no longer exist. And here's an object that's just as bright as the whole center of the galaxy. You'd think it's a star that's near in our galaxy that just got caught in the picture frame. It's not. It's a star on the edge of that galaxy that has exploded. And exploding stars shine with a brightness of 10 billion stars. They're the brightest fireworks in the universe, supernovae. And they're remarkable, and I keep having asides. Maybe I'll get to my point eventually. But this is something that I wrote a whole book about, and someone asked me yesterday why I wrote that book. Because it is the most poetic thing I know about the universe. Richard wrote a great book called, what's it called? Our Ancestors? What's it called? Ancestor's Tale, yes. I wanted to make sure I got that right. And I wrote a book that was a different Ancestor's Tale. It was called Adam. But the amazing thing is that every atom in your body came from a star that exploded. And the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You couldn't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution weren't created at the beginning of time. They're created in the nuclear furnaces of stars, and the only way they can get into your body is if the stars were kind enough to explode. So forget Jesus. The stars died so that you could be here today. Okay? And anyway, this is, you can't read this, but I can, which is what matters. Stars burn, and the rate at which they burn depends upon how big they are. Our sun will last about 10 billion years. It's 4.5 billion years old now. It's halfway through its life. 10 billion, so it has another 5 billion years left. Which, by the way, reminds me of actually the only real cosmology joke I know, so I'll tell it to you. So someone like me is talking to a group of people like you on a Sunday, and he says, you know, the sun is going to burn only for 5 billion more years. And someone in the audience goes, did you say 5 million years? And the speaker says, no, 5 billion years. And the guy goes, whew, okay. Anyway.
Thanks very much, Tony. I want to ask the panel, and in particular Lawrence Krauss. Australia has produced around 15 Nobel laureates, and every day about 1 billion people rely on Australian technologies, from the bionic ear to Wi-Fi to IVF, etc. Unfortunately, Prime Minister Tony Abbott and Treasurer Joe Hockey have used the first federal budget to continue their assault on science. In particular, the CSIRO has had to face a pull-out out of major research areas, and the Clean Technology Innovation Fund has been scrapped. What is this saying to the people? What is this saying to the people of my generation who want to pursue a career in science and become chemists, physicists, etc.? Does research really matter?
You know, it's a great question. It's a really important question, because if a government pretends they're interested in innovation and they stop funding, there's so much evidence that at least 50% of the GNP of most of the Western world is based on research and development a generation earlier. If you stop spending it, you're harming the economy down the road. And in fact, it's kind of amusing it's actually tragic. If you look at the cuts to CSIRO and the Australian Research Council and CRC, you add them up, those cuts are about equal to the money being spent on school chaplains over 4 years. And so you just say, in a country where you're supposed to be interested in the economy and improving the economy, you're taking away the fundamental basis of the economy, which is research.
But Lawrence,
and it's Australia's future. It isn't selling coal to China. It's if this country wants to be a major contributor in the future, it isn't getting rid of its resources now. It's developing the intellectual potential of people and creating things like Wi-Fi and all the things that CSIRO is doing. And moreover, CSIRO gets money from industry, and when the government cuts money to CSIRO, their matching funds from industry also go away. So it's not just the $110 million cut there. There's another $50 million that industry is now no longer going to provide them. It's a horrendous budget cut for a government that's concerned about the economy, it seems to me.
Just before I...
Lawrence, is there a possible future for intelligence, especially in a universe that we now know is not only expanding, but under accelerating expansion?
Well, if that acceleration continues, as I like to say, we live in the worst of all possible universes to live in for the future of life. So much for intelligent design. But you can show that among all universes that are continuing to expand forever, a universe which is accelerating, life will end in such a universe before it will end in any other universe. And that's even if you can avoid all of the tragedies that are going to befall this planet, for example. The sun is going to get brighter, and in 2 billion years, the Earth will then be in a zone where Venus is now, and the surface of the Earth will be about 1,000 degrees. In 5 billion years, the sun will expand and eat up the Earth, and lots of things, proton decay, all sorts of things are going to befall us. But let's say we're smart enough to get around all that stuff. It turns out that there are fundamental constraints on life, and therefore intelligence, in the very long term. We do know, for example, that for a long time, life can exist as we know it with intelligence that's powered by solar power, which is what our planet is, for at least, 1 trillion to 10 trillion years. Because there will be stars more or less like our sun that will be around for that long. There'll be life and there could be intelligence, but it won't be very happy. Okay, because especially if it's intelligent, because if the universe is accelerating, then the rest of the universe is slowly disappearing before our very eyes. Distant stars are moving away from us faster than the speed of light, and if we wait long enough, everything outside of our local cluster of galaxies will have disappeared.
But you go far enough into the future, and you wind up with nothing.
That's
you
what
wind up
like.
with a random photon every galaxy's space.
Oh, I know, but
or
if you're willing to be a science fiction aficionado or a very inventive physicist, you might say, "What do you mean? Big deal. Your sense of time could change, right?" So right now, a few minutes may seem like a lot, but in such a universe, you could have a living system where if it had a thought every 10 trillion years, that would seem normal. We have a pace of life that's based on really the energy available to us now. You could imagine living conscious systems which have a very different pace and therefore can extend out at least a lot farther than you'd imagine otherwise. All roads right now seem like they will suggest that life will end. But, see, I don't want people to get too depressed, because the nice thing about life is also the following. It's a fluctuation. It locally stores energy. In a universe that's getting more and more random, life likes to build up complexity. And so even if our life dies out, one could imagine at some time arbitrarily far in the future, a fluctuation occurs which allows intelligent life to exist again for a little while in a cosmic future, and then again and again. So you might have islands in time of intelligence. So even in a hopeless, pointless, miserable universe, there's something to look forward to.
My question is, do Christians have a special responsibility to respond to human-induced climate change?
John Dixon, let's start with you.
Yes. But most Christians accept the science. This is, I hope, one of the themes of tonight's Q&A. It's Christians get all the science Lawrence is talking about, plus all the other wonderful stuff. So it's not just that wonderful stuff or...
Some of them.
So, yes, we have a deep responsibility. I mean, there are some very deep ideas driving a Christian response to climate change. It's the science, we're schooled by the scientists, and then the Christian sits there thinking, this creation is actually a creation, an intended, beautiful work of art, and humanity is here to care for it. And more than that, that we're here to care for our neighbours, especially the neighbours that are going to feel the effects of climate change more than most, poorer communities. So there is, I would just say, a deeper or added dimension to the Christian care of the earth. Whether that's showing itself in church action is another question, but theoretically, Christianity should drive a very deep commitment.
But not a special one. I really object to this notion that somehow, look, I applaud that you get faith and meaning in your life from your faith. That's fine. I get faith, I get meaning in my life from my lack of faith, okay? I mean, the fact that I see the meaning in my life is the meaning I make. And the meaning for all of us, we're so lucky to be here on this planet and have brains and being able to understand the universe back to the earliest moments of the Big Bang and be able to impact on our future. And we should use those brains, and whether or not, and we shouldn't rely on someone else guiding us.
What I'm saying is, I get all of that. I get all of that.
But hold
Plus
on,
Jesus.
But the point is, that's fine. But the point is that doesn't give you any special. We are all humans. So you may get your meaning from your life from Christianity, but to argue that
And
you
science.
have, but
I get
to argue
science
that you have
plus
somehow an
Jesus.
addition that gives you
Okay.
more meaning in your life and more reason to take care of the earth is crazy. We all have the responsibility to take care of the earth, whether we're Christians or not.
God that we've created is not the kind of... I mean, you know, if you were a God, omnipotent, would you be so petty and jealous? Would you say, hey, let me get you to almost kill your son to see if you believe in me? Okay? Or... you know what? I want you to prostrate before me 5 times a day to show you love me. I mean, if you had an ant farm, would you kill the ants if they didn't look up at you every day and tell you how wonderful you were? Okay? I mean, it's just kind of, for an omnipotent being, he's pretty petty, or she. And even Christianity, which is supposed to be this loving religion, says, believe in me or go to hell for all eternity. Gee, thanks. Or, based on here's what I want to do. I'm going to kill my own son and torture him to absolve humanity from original sin associated with a non-existent forebear, Adam. I mean, it's nonsense.
Whether we're alone in the universe, in some sense, defines the universe for us. And as Carl Sagan said, if we're alone, it's an awful waste of space. But at some point, the question comes down to an interesting question of how rare is intelligence? I mean, it could be, and I happen to believe that since all the conditions for life exist elsewhere in the galaxy, water, organic materials, light, all of that life is ubiquitous. But the key question is intelligence an evolutionary imperative? Do all routes of evolution lead to intelligence? And on Earth they did. Well, at least one route did. And where it goes from here, we won't know. But that happened by a series of evolutionary accidents.
Isn't that a contradiction? Either evolution through its imperative causes intelligent life, or it's an accident. It can't be both. If it's an imperative,
well, I mean,
that sounds like theistic evolution.
Well, by imperative, I mean that all roads lead there, regardless of how random they are.
Wow, that's a powerful comment.
I don't know. I mean, I think all streams will go downhill, but I don't think they're being guided, other than by the force of gravity. And so are there physical laws that inevitably cause intelligence to be selected naturally in a way that allows, inevitably, if you have lots of different life forms, the intelligent life form will eventually come and dominate the planet, ruin the atmosphere, build huge cities, etc.
I know a whole bunch of theologians who could not have said that better.
Well, that doesn't say much. But I'm willing to believe that even if it's really rare, there's still a lot of intelligent life in the galaxy.
Well, what that brings up is Fermi's paradox. If you have all this time, billions of years in universal history, and you have billions of stars in our galaxy and hundreds of billions of galaxies, and now we know planets around maybe many stars.
Most stars, we think.
Have planets. Where are the aliens?
Okay. Well, we live in a random corner in the far edge of the Milky Way galaxy. Fermi's paradox is that, well, look, if life evolved, it would basically colonize the galaxy, and you could calculate it would send out robots or parts of its civilization to 4 other planets that would, instead of 4 other planets,
and if
everything would grow exponentially. It's not a bad logic, but I don't think it's inevitable. It's just as plausible to me that civilizations will exist where they are until they exhaust all the resources where they are, and then they'll move on. And even if they decide to send out lots of feelers, it's quite plausible to me that most of those feelers will not survive, whether they're robots or little colonies. And so this whole argument only works if civilizations decide they're going to colonize the galaxy. It's not so clear to me that it's inevitable that you have to colonize the galaxy. As I say, if most of
But
your...
you don't need most. If you could make the calculations on one or just a handful of civilizations that have a similarity to us that do want to colonize or have a need to colonize, and this expands exponentially, and then if you have the whole universe in
But you
so many
require
different
the
places.
exponential expansion. That's the key point. You require that each civilization send out a certain number of colonies, which then send out a certain number of colonies, which send out a certain number of colonies, and they all are sent out at a relative regular pace, and most of them survive. And we just don't know. If traveling through space is very difficult and deadly, and it's a long time, and lots of things can happen. And we also don't know, in my mind, if you look around at life on Earth, it's not clear to me that there's this imperative to always move. At the same time, as Fermi's paradox is certainly not illogical, but not necessary. Even if life is very rare, in an absolute sense, it can nevertheless be very abundant. It may sound ridiculous, but that's possible in the universe. I mean, it's a long shot that even if there's life out there, we'll ever know about it. That's the sad thing. But I also, at the same time, believe it's out there, and that's good enough for me.
Okay, Lawrence, one of the standing rules within the history of philosophy, especially over the last 300 years, has been that an is does not necessitate an ought.
Yeah,
that you
I
can.
heard
Well,
that.
no, okay, I understand that you might not agree, but you did make a very, very strong claim before in the course of your presentation that there is, in fact, a morality that is founded on science itself. Dr. Craig has said that science, that's actually part of the limits of science. You obviously disagree with that. I wonder if you could begin making, if you like, not so much the moral case for science, but why science has a morality inherent to it.
I would say morality is impossible without science. That's the point. Because, and religion is an example, as I say, I can't think of a more immoral document than the Old Testament. But the point is, if you don't know the consequences of your actions, then you can't even decide what's right and wrong. And so and so we have seen people's morality, if you want to call it morality, change. Slavery might have been okay because you might have believed that certain groups were inferior or not human. Science has told us that's wrong. You might have believed, as almost all religions do, that women are chattel. Science has told us that's wrong. You might have believed that homosexuality is evil. But science has told us that all mammalian species have homosexuality. There's nothing unnatural or evil about it. So to have a morality without science is empty. The beautiful features of the other theories is that quantum fluctuations, and there are an infinite number of them, could in principle produce infinite contributions, which would mean you couldn't calculate with those theories. But it turns out that there's a symmetry associated with those theories that causes those contributions to be manageable. You can ignore the infinities and produce predictions which actually work. It turns out in general relativity, because of its mathematical formulation, you can't ignore those infinities. At some level, the quantum mechanical contributions can't be tamed, and they produce nonsense. It really is just because of the nature, the mathematical nature of general relativity. And that's one of the features. The other is the conceptual problem of if space and time are the variables of general relativity as they are, then to have a quantum theory space and time is conceptually very complicated. But right now, that's not the problem. The problem is mathematical, that you have to make sure that infinite fluctuations in the gravitational field at very small scales don't screw up the theory, and right now they screw it up. That's why we're reasonably certain that general relativity is not the full story when it comes to gravity, that the theory will have to be modified, just like all other theories have been modified, as you go to ever smaller scales. There are two possibilities, that the theory will be modified by a quantum theory that is itself scale dependent, or that the theory will be modified by something like string theory, which produces an ultimate theory which describes the universe all the way down to the scale size 0. And you know, we're not talking about very much landscape here. We're talking about the scale where quantum mechanics of gravity becomes important is something like 10 to the minus 30 centimeters or so. And we're talking about, can you have a theory that describes the universe from 10 to the minus 30 centimeters down to 0? And as my friend, I think, Frank Wilczek has said about string theory, it's not a theory of everything, it's a theory of almost nothing.
In searching for this elusive final theory, string theory has now become the popular term. But what exactly is string theory?
Well, that's a really good question. I think many physicists are asking themselves the same question, and we're not sure we know the answer. At its heart, string theory really caught on in the 1980s because it's based on this idea that at a fundamental scale, elementary particles are not point-like objects, but rather one-dimensional objects, things that act like strings. Why? Well, it turns out if you allow that to happen, what was discovered was that that theory produced something that looked very much like gravity. And that's what caught people's imagination. Because you see, for most of the 20th century and so far, 21st century, gravity in all other ways has defied quantum mechanics. We tried to take general relativity and merge it with quantum mechanics and we get nonsense. But here was a quantum mechanical theory of a vibrating string that looked like it had gravity in it. So you might have a quantum theory of gravity.
And would it also produce this zoo of fundamental particles that experimentalists were finding?
Well, that's what got people even more excited, because initially you had gravity, and that alone was enough to draw a lot of people's attention. But then as people explored it, well, it turns out that those strings vibrating are only consistent not in 4 dimensions, but it turns out in a lot more dimensions. They got it down to 10 dimensions. After starting with 26, got it down to 10. And so vibrating strings at 10 dimensions would produce, in our 4-dimensional world, something that looked like gravity. Now you may say, well, that's a lot of extra stuff for nothing. But it turns out because of those extra dimensions, you also get a lot of extra stuff in the theory. And you might also get not just gravity, but the other known forces in nature, and not just the forces, but the particles.
Wow.
It looked in 1984 like you might have what, as they called it, a theory of everything. You might explain the entire observable fundamental structure of the universe, forces and particles, with a single idea, and everyone got very excited. And if life were an impressionist painting, then we'd be happy. The trouble is, as we began to explore string theory in finer and finer detail, a lot of the excitement, a lot of the hope, in some sense, has evaporated, because the models that looked like they might explain the 4 forces in nature and 3 families of elementary particles, those models, we realized, were not particularly good approximations to string theory. And then it turned out there were a bunch of different string theories, not one. And if you want to have a theory of everything, you hope it's unique, right? So there were a bunch of different ones, but they were discovered, well, they're actually all different manifestations of a single theory. Great. But not a single theory in 10 dimensions, a single theory in 11 dimensions. A theory called M theory. We don't know what M stands for, but it's called M theory.
What's one more dimension?
Yeah, but in this case, it turns out when you have that extra dimension and that theory began to be investigated, it turns out that strings themselves may not be the fundamental objects after all, just like particles weren't in 4 dimensions. Strings may themselves be an illusion. It turns out the dominant, most important things may have been things that weren't even known about in 1984, things called brains, like membranes. A three-dimensional universe would be like a 3-brain, 4 dimensions, 5 dimensions, 6 dimensions, and the dynamics of those things make the theory almost infinitely more complicated. And what's been discovered is that perhaps this theory may have nothing to do with reality, but even worse, maybe it does have something to do with reality, and there's no possible way for us to make a connection between that abstract idea in 11 dimensions. It's really not even yet a theory. It's an idea in search of a theory, because it's so complicated that we're realizing, for example, that it might not predict a single kind of universe like our own, but perhaps 10 to the 500 universes. And that can be viewed as a success or a failure depending upon how you're looking at it. If you can predict a universe that has any different properties you could ever measure, then that's like predicting nothing at all, right? Because if your theory is consistent with anything I can measure, then it's not falsifiable. It's more like philosophy than physics. If I can't prove it wrong, then I don't know if it's real.
But that doesn't mean it's not real.
That doesn't mean it's not real. The worst thing would be that if it's real and we couldn't prove it.
Well, I don't know why. I don't think that's the worst thing. If it's real, even if you can't prove it, accept it.
Well, how do you know it's real? I mean, maybe maybe instead of particles being made of strings, they're made of pink elephants. I mean, if you can't disprove the idea, then from a physics perspective, it's impotent. And if it's impotent, you ultimately end up throwing it out. I've said that string theory is the least successful great idea of the 20th century because it's been 30 years that it's been worked on by really smart people, thousands of them. And progress has been made, but we still haven't answered any fundamental physical questions about the universe. And we haven't shown that we can falsify it. But some string theorists have recently taken this idea of 10 to the 500 universes as a great success. Because as we look out at the universe, we've discovered it's kind of crazy in a number of different ways. There's certain properties like dark energy and other things that are completely inexplicable. Some people have said maybe there's really no fundamental explanation of why the universe must be the way it is.
Unique.
No unique
necessary.
It may just be an accident. Physics may be an environmental science. Our universe could be one of an infinite number of universes, in each one of which the laws of physics is different. And we live in our universe because our universe allows life. It's called the anthropic principle.
Very controversial.
It's very controversial and to some physicists very disgusting. But to string theorists, it seemed like the Holy Grail because it was a great resonance. Because here you had this theory that couldn't explain anything. And now you have this universe that may not be explainable. And the two work together very well because string theory has produced what they call the landscape. If there are 10 to the 500 universes, you have a natural landscape in which this idea of the anthropic principle can flourish. But the problem is, in some sense, you've gone from, instead of having a theory of everything, to a theory of anything, which some people would say is equivalent to having a theory of nothing. And we just don't know.
It'll be the new astrophysics of the 21st century. And we're building gravitational wave detectors to do just that because they'll allow us to see the moments of formation of black holes and collisions of black holes. And maybe, because gravitational waves are so weak, they'll propagate from the very early universe to now without being impeded. So they might give us a window on the universe when it was only a millionth of a billionth of a billionth of a billionth of a second old, which is pretty close to the Big Bang. We'd be able to see the formation of black holes. We'd be able to see colliding neutron stars. We don't even know all of the things we won't be able to see. Massive cataclysmic events where huge amounts of matter move around in an explosion or a collapse produce gravitational waves. And if general relativity is correct, in the final stages of formation of a black hole, huge amounts of energy should be released in gravitational waves, and we may be able to see them. In the moments where two black holes collide, forming a big black hole, or two neutron stars collide, forming a large single black hole, there should be huge numbers of gravitational waves produced. We'd be able to see that, and we'd learn about properties of general relativity and the regime of strong gravity, and we'd learn a lot about the nature of black holes and other astrophysical objects in the universe that otherwise we literally cannot see.
Lawrence, why is it that most good scientists don't believe in God?
Well, I think you're overstating it a little bit. I think that most scientists don't think enough about God to know whether they believe in him or not. It's just irrelevant. There's no evidence that we need anything other than the laws of physics and the other laws of science to explain everything we see. Physics has been so successful in describing the universe that we tend to be the most obnoxious among the scientists in terms of our chutzpah, in terms of assuming what we can do. In fact, often overstating the case that science is all there is.
Why do you say overstating the case?
Well, because I've come to realize over the last few years that it's really important to realize that science isn't all there is. We now can address with a straight face questions like why is there matter in the universe and what happened in the first billionth of a second. And so because of that grand sense of power, I think people tend to say, well, if we can understand things all the way back to the first billionth of a second, we understand everything. But science is not the only way of knowing. Many people feel some spiritual sense, and science doesn't address that. Some scientists would say because science doesn't address it, it doesn't exist. It's nonsense, you're fooling yourself. And that might be right. But if you can't test it, it isn't science. And there are lots of things you can't test. I think it is really important to recognize, as has been said, that science does not make it impossible to believe in God. It just makes it possible to not believe in God. And that's really important because until you had science, everything was a miracle. So science takes a tremendous amount away from being miraculous and says there's just a pedestrian cause, maybe a wonderful cause, but it's a natural cause. I was at the Vatican once and at the Pontifical Academy and lecturing to some theologians, and I said to them, and I wasn't being facetious, that they had to listen to me, but I didn't have to listen to them. Because in some sense, I think to have an honest and sensible theology, you have to be consistent with the laws of physics.
Right.
But I don't need to know anything about purpose or ultimate purpose of the universe to understand how it works.
But is there an area beyond which science cannot go, and even in principle cannot go?
Yes, of course, there is, and I would say faith in some sense. Faith being defined as that which you believe in with the absence of evidence. I'm always hesitant to make absolute statements because as we understand more and more about the history of the universe and understand whether our universe is unique, etc., we may come to grips with questions that have traditionally been theological ones. So I can't say that at some point we won't. But it is important to realize at this point what the limits are. And I think there's been a lot of interest in the interface between science and religion, and I find that unusual. Because I don't think there is much at the interface.
Hello, my question is for Brian. Your new program is about humanizing cosmology, but the history of science since Copernicus is about moving us away from the center of things. So how important do you think the human species is in the grand scheme of the universe?
It's a very good question. I mean, the demotion of the Earth from the center of the universe to what is undoubtedly an insignificant speck. You know, if you think about the fact that we've discovered there are 200 billion stars in the Milky Way galaxy, perhaps 350 billion galaxies in the observable universe. But in the series, I call that an ascent into insignificance, an ascent, because it's a tremendous intellectual ascent to move us from the center to actually measuring our coordinates in space and time. And
an ascent into insignificance.
Yes, an ascent into insignificance. It's an intellectual ascent into insignificance. And so, but the answer to the final part of your question depends on the previous question, really. How rare are civilizations? And of course, the correct answer is we don't know, except we don't see any evidence at the moment for them. We've listened a bit. We have SETI, Search for Extraterrestrial Intelligence, never detected a signal, never detected any evidence of any alien civilization. We haven't looked that hard. So I think that our value, to me, lies in the fact that a species has arisen on this planet that, first of all, has measured the age of our bit of the universe, at least, to 13.798 plus or minus 0.035 billion years. That's not bad in 400 years. We've gone from the center of the universe to knowing our place in space and time in 400 years, and that's impressive.